Welcome to a new video. In this video we will discuss the eigenvalues and eigenvectors. We will see how we can use the eigenvalue equation as shown here, where we see the lambda and the eigenvectors for a specific matrix. Of course, we will work out several examples step by step and show the calculations and verify these in MATLAB command window. Okay, first we will define what the eigenvalue and eigenvector is for a matrix. Now, if you have an n by n matrix, so it is actually a square matrix, so let's say 2 by 2, 3 by 3. If there is also a non-zero vector, in this case v, and also a scalar lambda, such that this equation is valid, then we have an eigenvalue problem where we can say that this v is an eigenvector and this lambda is the eigenvalue of this matrix A. So this is a special case. You can see also that this is a scaling operation. So the eigenvalue equation is given by this expression. Again, the matrix A is multiplied by some vector, in this case v, and that will result in scaled version of that vector v. So let's say 6 times the vector v. If this is the case, then the v is the eigenvector of this matrix A and the lambda is the eigenvalue of that matrix A. Okay, how can we see that pictorially, so in a graphical form? So we see here the vector v, let's say pointing in this direction, and if I multiply that by matrix A, some matrix, and if that results in a vector which is in the same direction, which is maybe longer or maybe shorter, it doesn't matter, maybe also reverse, but in the same line, then this, what we call here, then the v, is the eigenvector of that matrix. But we cannot say that for vector u. For example, if you have vector u and you multiply that again by the same matrix A, that will result in this sort of the rotation, and this is not the eigenvector of this matrix A because you don't see them in the same direction. So we can say the v is indeed an eigenvector of A and u is not an eigenvector of A. This is now graphically shown what's happening with these eigenvectors. Okay, now let's see an example. First example, we will see how we can prove that this vector 1, 1 is an eigenvector of this matrix given by 5, 1, 1, 5. So how do we do that? Now we can look in our solutions by looking at the eigenvalue equation. If this holds, then this is indeed correct. So the equation is given by this, so you have an A times this vector must equal to some scaled value of this vector v. If this is true, we can say this is indeed correct. So we have 5, 1, 1, 5, and we have here 1, 1, which is the vector v. If I now do the matrix times the vector calculation, you see here 5 times 1, which is 5, and then plus 1 times 1, which is 1, so you'll get a 6 here. That's the first entry in a similar form, 1 times 1 plus 5 times 1, which is again 6. So you see here 6 and 6 as a new vector, but this is actually 6 times this 1, 1. So you see the vector v is again appearing, and there is also the eigenvalue here, which is associated with that vector. So in this case, the eigenvalue is 6. So it is indeed correct. So we can say that 6 times this given vector. Now, thus we can write the eigenvalue equation like so, and if this is correct, we have proven our situation here. We can also see that in MATLAB, this is the given in MATLAB in the command window. You can define a matrix like so, 5, 1 and a semicolon, and you go to the next row and a 1, 5. So this is the definition, how to define a matrix in MATLAB. And this is the vector we have given, so 1 and 1, so 1 semicolon and then again 1. And then we have here this, and this we will now operate like eig. This is the eig, meaning I calculate the eigenvalues of this A, which is indeed 4 and 6, so one of the eigenvalues was 6, so it's indeed as calculated. And if I do A times V, which is this left side of the equation, I end up to 6, 6, which is actually as we have calculated, so this is also correct. Okay, now let's look at another example. Now we need to prove now in a different way that the 5 is an eigenvalue of this new matrix A. So 1, 2, 4, 3. How do we do that? Again, we look at the equation of the eigenvalue problem. So the eigenvalue equation again needs to hold. And in this case we need to find the 5 or use the 5 to determine this is indeed an eigenvalue. Now we can replace this equation lambda times v to the left side, and when we do that we need to also be careful because we see on the left side we have a matrix times a vector, so we need to also have a matrix here. So we can do that by just multiplying the scalar by the identity matrix like we do in the scaling, just multiply by 1. It doesn't have any effect, but in order to stay in the same dimensions we have to do that. So it is the matrix times the vector. In this case it's also matrix times the vector. Now the right side will be 0, but it's not just a 0 as a scaling or a scalar, it is a 0 vector. So we need to also make that clear here. Now next operation is we need to calculate here the lambdas, or use the lambdas in order to see that this is indeed 0. One important thing we need to consider here is the following. We know that if this equation must come up to 0, or if this equation of the eigenvalue problem needs to hold, that means we have a linear dependent operation, meaning that our determinant is 0. So there is some dependency between the rows and the columns. Okay, so we can write it like so. This is the second row equation. We can write it like so, because we can now have the v out. And we have now also 5 here for lambda. Now we need to now solve this equation. If I want to solve this equation, I can now do the elimination. First, before we do that, let's first calculate what is now a minus 5 times I. And I here is the identity matrix, 2 by 2. So 5 times I, and a minus 5 times I. You see here 5 times this identity matrix, and this is our matrix A. Now we do multiplication of this 5 here inside, so every entry will be then times 5, you see that here. And then you do element-wise subtraction, so 1 minus 5, 2 minus 0, 4 minus 0, 3 minus 5. So this is actually the 4 operations. And then you get here, as mentioned, the new matrix is down. This matrix in the parentheses will be then minus 4, 2, 4, minus 2. Now we need to solve this. That means we need to look at the row reduction of this matrix. We make that or augment it with this 0 vector, which is shown here. And now we can see that this is indeed linearly dependent system or set of equations. Now we see here the row 1 and row 2. And if I now do row 2 plus row 1, that means 4 plus minus 4 minus 2 plus 2, I end up actually with this equation, which is shown here. 0, because this is 0, if you add them up, this is 0, if you add them up, this is 0, if you add them up. And now we see here indeed, there is no pivot in the second column. So we can say there is a free variable. In this situation, we have the free variable in the second column. So this 5 is an eigenvalue of this matrix A. This is the way to prove this. Now let's go now to the matrix, the MATLAB, and the command window. Again, our new matrix A, 1, 2, and then semicolon 4, 3. Now we also, this is the definition, we define here the matrix and we calculate here the eigenvalues of this matrix. You see here minus 1 and then 5. So there is indeed this 5 here. Of course there's another eigenvalue because we have here 2 by 2 matrix will have also 2 eigenvalues. If you have 5 by 5 matrix, you will have 5 eigenvalues. So this is indeed as we have seen. So we have also proven that using this operation. Now let's go to the example number 3. In this case, we have only the matrix given. We want to have the eigenvalues and eigenvector. So there is no eigenvalue given or eigenvector. So we just actually start from just this matrix. So how do we do that? Again, we look at the eigenvalue equation, which is this one. And now we need to really solve this for both situations, which is the eigenvalue and eigenvector. Now we can write this again as we have done it before. So we'll put this to the left side with the identity matrix and then keep at this right side this 0 vector. And then we need to look at the determinant, because we already said that if there is an eigenvector, that means there must be a linear dependency. So that means if this must be linearly dependent with this vector v, I need to have the determinant of this one be 0. So if I define that, then I can find the unknowns lambda. So that means if I look at my matrix A, I do then minus the lambda times I. That is actually in effect only minus in the left top and the right bottom. So you do 5 minus lambda, 2, 1, 6 minus lambda. Because this lambda will be then multiplied by this identity matrix, which is 2 by 2. Now we need to solve this. So that means make the determinant of this one, set it to equal to 0 and solve it. Now what is the determinant? The determinant is you multiply the element here with this one and then minus 2 times this one. Then that is actually shown here. So you see here 5 minus the lambda in the parentheses times 6 minus the lambda minus 2. Now we need to work it out. This is just a second order equation where you need to find the unknowns, in this case 2 lambdas. So we can work it out, the lambda. So you see here lambda squared, and then here for also minus 11 lambda, and also 6 times 5, so 30, and we have also minus 2. So we have effectively lambda squared minus 11 lambda plus 28, which is shown here. Can we factorize this? Otherwise we need to use the formula for this quadratic equation. We can do that because we have minus 4 and minus 7, because if you add them up it will be minus 11, and if you multiply these two numbers will be plus 28. So this will do. And if you solve this, you get here the solution. Lambda must be 4 or lambda must be 7. So we have here, by the way, our eigenvalues already, lambda 1 and lambda 2. So you can number them 4 and 7. Okay, now the first job is done. Well, now we need to go to the eigenvectors and we need to find them for each eigenvalue. So let's start with the eigenvalue lambda 1 is 4. How to do that? Now we look at the our matrix and then we subtract that from the identity matrix, which is multiplied by this lambda, and then we do the row reduction, the Gaussian elimination. So first we do this, which is now here again given his top left and right bottom. You subtract now specifically this lambda because we did it here in general, but now we know which lambda does the job. Now we have here 4 and also 4 here. That means 5 minus 4, 6 minus 4. The other two will be the same. Now this is 1 and this is 2. So we end up to actually this one. And you already see that this is indeed linearly dependent because the same row. And that can be done also making row reduction, like row 2 minus row 1. We will have 0, 0, 0 here. And now we see it clearly that it is indeed no pivot in the second column, so we can say there's a free variable, and I call this in this case x2. So if you have x1 and x2 as unknowns, we can say our free variable is x2, and we just give it some letter, in this case t for example, and that is element of the real values except 0. Now we can also say if this is t, so if it is set to t, what is then the x1? Now if I look at this one, it will be x1 plus 2 times x2 must add up to 0. That means x1 is equal to minus 2 times x2. That's actually shown here. That means since we have defined this x2 as t, this is minus 2t. We can bring these two together and then make a vector x where we have this x1 and x2 in it. So x1 is minus 2t, x2 is t. That means actually minus 2 and 1 and a t outside. This is now the general vector, and if you make it specific, in this case for our situation, you can just select any value for t except 0. You can say if I now take t is 1, I have now my eigenvector, in this case will be minus 2 and 1. So we have now found the corresponding eigenvector for this eigenvalue of 4. Now in a similar case we will do that for eigenvector for lambda 2 is 7. Again, we proceed with this equation by doing now lambda 2. Now you subtract here lambda 2 and lambda 2, and now you do that of course with 7. Now you get here a minus 2 and minus 1. Now we need to look at how we can proceed in order to get here zeros. So all of them zeros, so the linear dependent form. I need to do the row 2 minus, plus the half of this row 1. So if I do row 2 plus the half of this row 1, I have indeed what I want, because the row 1 is not changing, but the row 2 is changing, because this will be 0, this will be 0, and this will be 0. That's all here. Again, we have free variable. Again, there is no pivot in the second column, so we need to say x2 is some letter. It can be also some other letter if you would prefer. And then there's again an element of the real values except 0. So we have then also x1 is equal to x2. Why? Because this is here minus 2 times x1 plus 2 times x2 will be 0. That means minus 2 times x1 will be, if this is placed on the right hand side, will be minus 2 times x2. So x1 is effectively x2. Now taking this all together, then by the way also t. So taking these together in this new vector x with the x1 and x2, that will be then 1 and 1 with the t outside. Again, we can now make our eigenvector for this eigenvalue and then specifically choose our t as 1, and we have now here 1, 1. Now we have also the v2, so the v1 and v2 are our eigenvectors. But let's check now the results here by applying this eigenvalue equation right away. So we can say there's a matrix A and we multiply it by this vector, and if we will see if this is indeed correct. So our matrix here 5, 2, 1, 6 times minus 2 and 1, which is our vector v1, that will result in 5 times minus 2, which is then minus 10, plus 2 times 1 will be minus 8. And then the second element here in this vector will be then 1 times minus 2 will be minus 2, plus 6 times 1 will be then plus 4. Now when you now rewrite this like 4 times minus 2 and 1, which is then just divide each element here by 4, you see indeed that this is the lambda 1 we have calculated, and this is indeed v1 we have calculated. So this is indeed correct. Let's also check that for the second lambda and the second eigenvector. So again, we use the eigenvalue equation and we do the matrix A times the v2. Now 5 times 1, 5, plus 2 times 1, so plus 2 will be 7, and 1 times 1 plus 6 times 1 will be 7. But you can also write it down like 7 times 1, 1, which is the eigenvalue here. You see it appearing, so you can also see that here, and this is the eigenvector v2. So this is also indeed correct. Okay, let's also check that in the MATLAB command window. Now we again here define our matrix 5, 2, 1, 6, and this is then the matrix given, and here we calculate the eigenvalues of the matrix A, and you see here 4 and 7. So this is the result, and this is also a result as shown here. So we have also verified this in MATLAB. Alright, this was our example considering the eigenvalues and eigenvectors. We have briefly discussed the definition of an eigenvalue and eigenvector, and we have worked out here 3 examples considering this eigenvalue and eigenvector problem. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.